Hey y'all, my name is Prashant Kumar, or PK, and I'm an MCAT tutor at Shemmassian Academic Consulting. Today, we're going to be doing a passage walkthrough in the MCAT Chem Phys section. You should be taking roughly 6.5 minutes on this passage, but today, we're going to be going more in depth so you can see exactly what's going on in my head as I take on this passage. Let's get it. Alright, great. So I've gone ahead and put the passage on the left and the questions we're going through on the right. So feel free to take a moment and pause the video and come back to us when you're ready. If not, let's get right into talking strategy. For me, I like to maintain the same strategy regardless of what passage I'm looking at. The reason for this is it gives me some sort of routine to come into a passage with. Regardless of whether the passage is super easy or super hard, I know I have something to come back to make sure I understand what's going on. Oftentimes I feel like stressed out if there's a super hard passage and I'd waste time being stressed or I'd lose confidence in my ability. So doing something over and over again builds that routine, builds that confidence, and makes you geared up for test day. So for me, that strategy is read the paragraph, write a quick 3 to 5 word summary, go on to the next paragraph, do the same, and on and on and on. The reason I really like this strategy is that it provides accountability, making sure you have a quick check-in after each paragraph before moving on to the next. I'd find myself a lot of times sort of reading words and not understanding what's going on, and then continuing throughout the rest of the passage and not understanding what's going on and having to reread. And preventing this with this little check-in, saying, do I understand what's going on? Provides an ability to not waste time. And if you need to reread, you can reread that paragraph alone. You don't have to reread the entire passage. So it saves a lot of time in the long run. My second piece of advice is look at the figures, but don't spend too much time on them on the first read. We don't know what the questions are going to ask about the figures, if any, right? So why would we waste time before we need to? And so with that, we have both of our strategies and we can get right into the first paragraph. Most biochemical reactions depend on the pH value of the aqueous environment, and many are strongly favored to occur in an acidic environment. A non-invasive control of pH to tightly regulate such reactions with defined start and end points is a highly desirable feature in certain applications. All right, so the question I ask myself after each of these paragraphs is, what's happening, right? 3 to 5 quick words, easy words, anything, right? We just want to understand what is happening in basic terminology. So here, all I'm saying is pH control reactions, right? Good, check. That's what I'm saying. You can write abbreviations, arrows, whatever you want, right? Mnemonics. These notes are supposed to be for you and you only. No one else is going to look at them. So abbreviate, do whatever you need to do to save time as long as you're getting what you need out of it. So here I'm just thinking, oh, it's talking about pH controlled reactions and how they're very important. So I just put a check mark by that. Next paragraph. Researchers report a novel optical approach to reversibly control a typical biochemical reaction by changing the pH by using an acid phosphatase as a model enzyme. The reversible photoacid G acid functions as a proton donor, changing the pH rapidly and reversibly by using high-power UV LEDs as an illumination source in the experimental setup. The researchers found that the reaction can be tightly controlled by switching a light on and off, making the technology applicable to a wide range of other enzymatic reactions, thus enabling miniaturization and parallelization through non-invasive optical means. Figure 1 displays the structure of the G acid, and then it gives us a figure. So again, what is the question we're asking, right? The question we're asking is what's happening? And so here, there's a lot going on, right? It's giving us a lot of words, a lot of things we might not have heard, right? I always note like words I've never heard before, like miniaturization and parallelization, right? Things I probably haven't learned before. So we're not going to focus too much on those because those are more detail oriented. Instead, we're thinking about, what are they looking at? Well, they have this sort of LED functioning for sort of acid phosphatase pH reaction, right? And so that's all I'm thinking, right? We have these LEDs that are functioning in some aspect to change pH rapidly, right? And then we're looking at acid phosphatase, all of that, but these are details. We want to focus on big picture understanding. So LEDs are affecting acid phosphatase reactions. That's the big takeaway. And then we look at the figure, right? And we see some sort of reaction. I always look at the little blurb underneath. So figure 1, light activated deprotonation of G acid, right? So we're looking at what happens when we add light to this reaction and this protonation. But again, not spending too much time on that figure. We don't know what's going to be asked, and we can come back if needed. All right, onwards. In order to use the photoacid in a wide range of biochemical applications, the researchers ensured that it met certain requirements, such as solubility in water, low toxicity, and excitability with commonly available inexpensive illumination sources, such as LEDs. LEDs have several advantages compared to more conventional illumination sources. They are more efficient, have a long lifetime, a compact size, and high reliability. All right, so again, what is happening? Quick question, right? So here they're deciding, okay, when are we going to use these photoacids, right? And so I'm just going to call this, my paragraph, the photoacid criteria, right? And so then I'm going to point that has to do with LEDs, right? And so this is all I'm saying, right? It's talking about why we're using LEDs, and then it suggests why LEDs are great. And so a quick 3 to 5 word summary and onward. The researchers chose an acid phosphatase as a model enzyme to further study the system. The activity optimum of APs typically lies at an acidic pH of 4.5 to 5.5. APs non-specifically catalyze the hydrolysis of monoesters to produce inorganic phosphate under acidic conditions. In experiment A, researchers used the acid phosphatase from potato, EC 3.1.3.2, which is active between pH of 4 and 7, with an activity optimum at a pH of 5 and 5.3. At an alkaline pH of 8, the activity of EC 3.1.3.2 is several orders of magnitude lower. All right, so a lot of details here. Again, we're not focusing on what's happening. We're just focusing on like a big picture understanding. So here we have sort of like an experimental design, right, where we're looking at these acidic pHs, right, or these APs at different pHs, right? And we're using that to model like a system. And we don't need to know every detail, right? We're not focusing on catalyzing the hydrolysis of monoesters or whatever, right? Here it says that these acid phosphatases are more active at certain pHs than others, right? It says it's optimum at 5 to 5.3, and then several orders of magnitude lower at alkaline pH of 8, okay? So if you want to add acid greater than basic, something like that, just to note that the 5 to 5.3 is where it's optimum versus the pH of 8, then you can note that too. But remember, this is whatever you need, whatever you can stay quick with. All right, onward. To assay EC 3.1.3.2 activity, researchers used p-nitrophenyl phosphate, PNPP, assay. The PNPP assay is a colorimetric assay in which the substrate PNPP is hydrolyzed by acid phosphatase in the product p-nitrophenyl, PNP plus PI, and purified HPLC grade water as shown by figure 2. Okay, and then we have a reaction PNPP to acid phosphatase PNP plus PI. All right, so here there's not much there, right? It's just describing this different assay, looking at PNPP assay, right? And so then I'm just going to point it to this because it gives us exactly what the paragraph is saying, right? What are we inputting? What is it outputting? And how is it occurring? Okay? And so we're not spending too much time on the figure. It's just a reaction scheme for this assay, okay? And with that, we've done it. We have gone through our passage and sort of mapped it out, and we understand big picture understanding of what's happening. We're sort of looking at pH-dependent reactions, especially around this very important acid phosphatase, and then we have this assay that looks at it as well. And so with that, we're ready to get right into questions. And so we'll start with question number 1. Which of the following best describes the role of water in the deprotonation of the G acid? Is it A, acid, B, catalyst, C, base, or D, an aprotic solvent? Okay, so where would we look to see the deprotonation of a G acid? Well, we remember that when we saw the second paragraph, it's talking about the reaction occurring with this UV light and water being the the place where this deprotonation occurs, right? It says plus H2O. And so we see that the photoacid, right, the reversible photoacid G acid is a proton donor, okay? And so here we have a reaction that has to do with a proton donor and a proton acceptor. And so right away your mind should be thinking, protons are being traded between molecules. This is a commonly seen type of acid-base reaction, right? And so since there's only two molecules here, right, there's water and there's the G acid, right? We know those are the two acid. One's the acid and one's the base. And so right away we can get rid of catalyst and aprotic solvent. Aprotic solvent is where it's occurring. It doesn't really make sense in this situation. A catalyst is something that's not used up, and it would stay the same throughout the entire course of the experiment. And as we can see, the H2O is turning into an H3O and is part of the reaction. So the catalyst is eliminated. And so now we need to determine which one's the acid and which one's the base. And that requires understanding the definition of an acid. An acid is always going to be your proton donor, right? It's going to want to give away an H+. Whereas your base it's like the grabber. It wants to have the H+. So proton acceptor and adds an H+, basically, right? And so here it's asking us the role of water, not the role of the G acid. So to get this question right, all we need to know is what's happening to water. Well, it's turning from H2O to H3O+. So we're adding an H+, and so that means what? That means water is our base. And so we've eliminated A because the acid would be this one, right? It's giving away the H off the OH and putting it on the H2O. And so that's the base. Great. And so with that, we're 1 for 1. On to the next question. Let's go. Question number 2. The researchers measure the energy of a photon during an experimental trial to be 3.3 times 10 to the negative 12th joules. What is the frequency of the wave? Note, Planck's constant is equal to 6.6 times 10 to the negative 34th. Is it A, 2 times 10 to the 22nd, B, 1.5 times 10 to the 22nd, C, 1 times 10 to the 22nd, or D, 0.5 times 10 to the 22nd? All right, so this is a standalone question, so we're not really going to need anything from our passage, right? It's giving us information, energy of a photon, the energy, and it's asking for frequency, and it gives us Planck's constant. So right away, we should be thinking of one equation off the top of our mind, and that is energy equals Planck's constant times the frequency, right? E equals hv. Very, very common equation. Very, very common on the MCAT because it's a simple plug and chug equation. And so right away, we can see that where we want to plug in our numbers. And so E, energy of the photon, is going to be 3.3 times 10 to the negative 12th joules, right? And we're equal to H, our constant, 6.6 times 10 to the negative 34th, right? Times V, or our frequency. And so all with this, we have an equation with one variable left, right? And so now we can start our math. And it's pretty simple based on algebra, right? If we want to isolate our variable here, all we do is going to say, okay, we're going to divide both sides by 6.6 times 10 to the negative 34th. So 3.3 times 10 to the negative 12th over 6.6 times 10 to the negative 34th. And I know, everyone's going to be like, oh, I hate these types of calculations. They're so annoying, especially in scientific notation. I'm here to give you some tricks. The first trick is to note right here that all of our answer choices end with 10 to the 22nd, right? So because of that, we're actually only doing half the work. We don't need to do the second half of the calculation. So we can kind of ignore the 10 to the negative 12th and 10 to the negative 34th because we know the answer will all end with the same scientific sort of exponential part of it, right? And so now we're left with V equals 3.3 over 6.6, right? And so 3.3 divided by 6.6, that's a little more challenging of a calculation, but let's just break it down into what we know, right? Well, if we can divide the top and the bottom by 3, that's 1.1 over 2.2, right? 1.1 over 2.2, that's just 1 over 2, right? And so while you might not note 3.3 over 6.6 is one half off the top of your head. Sort of doing this quicker sort of breakdowns into smaller terms that you're more familiar with can help you identify that that's equal to 1 over 2. Hopefully you can get that immediately, but if you can't, no worries. We're trying to make tips to help you get there. So 1 over 2, and what is 1 over 2 as a decimal? It is 0.5, right? And so now we're looking at any answer choice with 0.5 written in it. And there's only one, and that's D, right? None of the other answer choices have 0.5 in there. And so with that, we've used all of our sort of calculation techniques to get D without having to do like every single calculation. You want to use all the shortcuts and things you can do to get you there. And so with that, we are on to question 3. All right. Which of the following functional groups is not found on the protonated G acid? Is it A, alcohol, B, benzene, C, sulfonate, or D, sulfite? All right, so we're first identifying that it's a not question, right? Not means everything except this is seen. And we're looking on the protonated G acid. So where is the G acid talked about? It's that same exact second paragraph right here, right? So we can look at the figure and then we just are looking at the molecule itself, right? So now we need to decide which side is the protonated G acid. Is it this one or this one, right? And so it's pretty obvious a protonated one will have the proton on it. So that would be this guy. And so we're looking here to determine what functional groups are on that. And so this is exactly where you're going to need to know all your functional groups by heart. Hopefully those orgo skills are still fresh in your head, but we're identifying them. So let's start one by one, right? Is it A, alcohol, right? We see it right here. An alcohol is just an OH group attached to other things, and that's right there. So we can eliminate A because we're dealing with a not question. A benzene, right? What is a benzene? Classic benzene ring, sort of an aromatic ring with 3 double bonds, and we have that right here, right? And so we can eliminate B, okay? A benzene, I'll write them right here, benzene right there. And then sulfonate. Okay, so sulfonate is a less commonly seen one, right? But it's still very important to know. And a sulfonate is an S with a double bond O, a double bond O, and an O minus, okay? And then there's an R group attached to it, or additional carbons attached to it. So as you can see, it's SO3, 1 minus, okay? And then we have sulfite, another not as commonly known one, but what is that? That is S with a double bond to an O, and then an O, and then an O, both with minuses. So this is SO3, 2 minus as the functional group, and this is SO3, 1 minus as the functional group, where that double bond is determining whether it's a sulfonate or a sulfite. So with that, we need to identify which one of these is it. Is it a sulfonate or a sulfite, right? And so we see that there are 2 double bonds, right, on both of these. These are identical molecules, and they have 2 double bonds and 1 single bond, and that matches with our sulfonate, okay? So with that, we choose sulfonate as our answer, and we get rid of, sorry, I misspoke, exactly what I was saying. The not, right? We have a sulfonate, we have a sulfate. We don't have a sulfite, right? This is exactly the type of mistake that I don't want you to make. So good job catching me right there. But right, the sulfonate is what's eliminated, and the sulfite is what's not on the protonated G acid. I was testing you, obviously. But we're onward to question number 4. Researchers are likely to observe which of the following during a PNPP assay for EC 3.1.3.2 when pH is lowered to 5. Is it A, cleavage of EC 3.1.3.2, B, an increase in inorganic phosphate levels, C, a decrease in sulfonate levels, or D, a decrease in EC 3.1.3.2 activity? All right, so the question is asking sort of what happens to this assay at a specific pH. That's the basic question, and it gives us a bunch of answer choices. So we need to run back to the paragraph where we're talking about this EC 3.1.3.2. And where is that? That's in these last two paragraphs, right? Where we're talking about assaying 3.1.3.2 and sort of where it's optimally active, okay? And so right away, we should note that when we're talking about a pH of 5, we noted down in our sort of quick summary that it's very active at acids, right? Why? Because the activity optimum at a pH of 5 to 5.3, right? So when we're changing our pH from our pH of 8 to 5 to 5.3, we're at our optimal level. And so what does optimal activity mean? That means you're going to have an increase in the activity of your phosphatase, right? And so our acid phosphatase is exactly what we're looking at, right? We're looking at EC 3.3.2, and that is the activity that's being changed. And so if we're at optimal activity levels, we're going to have increased activity. And so what does that mean? Well, now we can look at this sort of reaction that's occurring with this acid phosphatase, and that's this one right here, right? We see the assay is a function of PNPP turning into PNP plus PI. And so with that, what would happen if we had increased activity? Well, that would mean we're moving in the forward direction, right? We're moving this way, more so than backwards, right? We're increasing the amount of reactions that are occurring. And so with that, that would mean what? If we're moving in the forward direction, we're going to have decrease of the PNPP and increases of the PNP plus PI. Because whenever we have a PNPP, then it's going to immediately turn into a PNP or a PI because it's at much greater activity level. And so with that, we're able to identify what's going to happen in our answer choices, right? And so we should be able to eliminate D almost immediately, right? We would expect an increase in EC 3.1.3.2 activity when we are decreasing the pH to 5, right? If we're moving to an optimal activity point, then we wouldn't expect a decrease. And then additionally, we see the opposite, right? We see an increase in the inorganic phosphate levels, right? And this is what we see with our arrow right here. Our PI, the notation for inorganic phosphate, is increasing because we're at the optimal activity level. And so with that, B is looking like our best answer right now. Let's look at A and C. Cleavage of EC 3.1.3.2. Well, we know that we're not dealing with cleavage right now, right? Acid phosphatase is a type of enzyme, and EC 3.1.3.2 is an enzyme. And enzymes aren't being cleaved at all. They're helping facilitate a reaction. Instead, it's the PNPP that's being cleaved into PNP plus PI. And so we can eliminate A. And then C, a decrease in the sulfonate levels. Well, we can see from even our first reaction that it's never going to be the sulfonate that's changing, right? It's the protonation and the phosphate group that's always changing. And so there's no effect on sulfonate levels, so we can eliminate C. And so with that, we have answered all 4 of our questions, and we've crushed it. Great work, team. We crushed another MCAT Chem Phys passage. Kudos for you for getting it done. Lots of great stuff dealing with organic chemistry, experimental design, some physics in there. Lots of great topics. Great job. If you like this video, give us a like down below and subscribe to our channel. And comment exactly what videos you're looking forward to next so we know how to prep for you. Additionally, check out our 528 strategy series on the channel from Vikram. Super helpful tips and tricks to help you get your maximum score possible. And finally, click the link in our bio for an MCAT question of the day every single day so you don't miss out on any studying before test day. Happy studying, and let's get it.